How many valence electrons does this molecule have? 31, 34, 38 valence electrons, or is there not enough information? We'll say this right off the bat. We definitely have enough information to figure this out. And there's actually two ways we can figure this out. If you're more of a visual learner, you might resonate with the stick and dot method, or if you're more a math person, then the molecular formula route is the way to go. And just to clarify, this is not the actual molecular formula of this molecule, it's just an example. However, no matter which pathway we decide to go down, because our molecule is in bond line form, a summary model, we need to convert it into a Lewis structure to reveal the missing atoms and features. If we look at this molecule up here, all of the ends and bends are carbons, and they may or may not have hydrogens attached directly to it. Likewise, the ends and bends of this molecule are carbons as well, so there are 5 carbons total for this molecule. 1, 2, 3, 4, 5. By nature of its properties, each atom of carbon will form exactly 4 bonds, but it's clear from looking at this diagram that none of these carbons appear to have 4 bonds. And broadly speaking, that goes back to the fact that a bond line structure is a summary model that doesn't illustrate all the features of a molecule, because each of these carbons does in fact have 4 bonds. It's just that we don't see all of them. Specifically, we only see the bonds between carbon and carbon, as well as between carbon and oxygen. This carbon right here has 4 bonds, but it appears to have 1. And hydrogens are going to make up the difference. So if this carbon has 4 bonds total, and one of them is a carbon-carbon bond, the other 3 bonds are single bonds with hydrogen. In fact, we can use this equation right here to do the same thing for each of the carbons. The number of hydrogens attached to any particular carbon is equal to the number of bonds it has, 4, minus the number of sticks it has. Use this equation for each of the carbons, and we reveal all of the hydrogens in this molecule. And with that, we've gotten to the point where we have all of our atoms and each respective amount to know what the molecular formula is. C5H12O. And for clarity's sake, there is a single bond between the O and this H. It just so happens that the group an element belongs to tells us exactly how many valence electrons that element will have. So hydrogen is in group 1, carbon is in group 4, etc. Therefore, each hydrogen contributes 1 valence electron, each carbon contributes 4, and each oxygen contributes 6 valence electrons. So if a single carbon has 4 valence electrons because it's in group 4, and our molecule has 5 carbons, carbon will contribute 20 valence electrons to the overall molecule. Hydrogen, on the other hand, contributes 12 because there's 12 of them, and each individual hydrogen contributes a single valence electron. So with carbon and hydrogen alone, we already have accounted for 20 plus 12 equals 32 valence electrons, and we haven't even gone through oxygen. So we'll get rid of answer choice A because we're already past 31 valence electrons. We do the same product and quantity of group number for the remaining element, oxygen. Add everything together and we get that 38 valence electrons belong to this molecule. So C is our correct answer. We've just figured this out using the molecular formula equation, but as I briefly mentioned, there's another way that we could do it, the dot and stick method. Here's the Lewis structure we found before, and we can see all the sticks, but where are the dots? Do we even have any dots? Well, it turns out that we still don't have a complete Lewis structure like we see right here where we can actually see these dots. And I can tell you that our molecule of interest does have dots. The great news is that because we haven't otherwise indicated any charge, we assume that all of our atoms have a 0 formal charge. And the other great news is that carbon and hydrogen with 0 formal charge have no dots, have no lone pair electrons. Oxygen, however, does. And the way that we figured this out is using this equation right here. It's actually the formal charge equation that's flipped around to solve for the number of dots. Group number minus number of sticks minus formal charge. So let's try this out. Oxygen is in group 6, minus there's 2 sticks, this one right here, minus a 0 formal charge. So therefore, each oxygen has 4 dots. And there's 1 oxygen. So there are 4 dots present. And now we're going to count up all the valence electrons using the fact that a single dot is a single valence electron, but a single stick is 2 valence electrons. So it's just kind of like a counting game, 2, 4, 6, 8, all the way to 34, 36, 38. And we also get that there are 38 valence electrons. So both methods show that we have 38 valence electrons.